Okay, everybody. Good morning and welcome. Today is when we start the last chapter of the book that you're responsible for this final exam on December 15th, called Mechanical Waves. But I do want to start off by, first of all, introducing Joanna again, who's got the wireless mic. Joanna, anything on there we should know about, or you okay? Okay, just let me know if there are. There was actually a question that I saw that I did respond to, but I think I might as well talk about it a little bit now. So let's go through again this derivation of simple harmonic motion for a pendulum, which was, if you look at this mass, if it's like a point mass on a massless string of length L, then the rotational inertia is just ml squared, and you get this equation for rotational acceleration. The negative sign means that if theta is clockwise, then the acceleration is counterclockwise. It brings it back towards the bottom. Or if theta is counterclockwise, then it's going to be, then alpha will be clockwise. It's opposite. So this is what's called a restoring force or restoring torque, or in this case, this is an acceleration always directed towards the 0 point there of theta, where theta is measured 0 at the bottom now. So then, since we certainly don't know how to solve this equation, there is no solution for this equation. What we do is we make the small angle approximation. And then we have this equation, which we do know how to solve this one, which is that if you just pretend the theta is an x and the alpha is an a, then we know that that's simple harmonic motion. And there's that trial solution that your calculus professor writes on the board. And in that case, we know that the period is 2 pi times the square root of whatever's in the brackets there. There's some kind of constant in that top equation. It's multiplied times the theta. In this case, it's g over L. So it's a square root of 1 over that. Times 2 pi is the period. So that's sort of analogously how we solve that. But the question on Ed, which is a great question, which is what counts as a small angle to make the small angle approximation? So my answer to that is that, well, it just depends on how big an uncertainty or an error you mind making. So this period, for example, 2 pi square root L over G, you can write that down to 2 significant figures or something like that, but it might be wrong. And the kind of wrongness of it is just how wrong your small angle approximation is. So let's say the maximum, let's say you keep theta to like 10 degrees or less. Well, in that case, what is the percentage, I guess, error in doing that? Well, you can first you have to convert to radians. So I think 10 degrees is 0.17. So sine of 0.17 minus 0.17, kind of divided by 0.17, you get 0.5%. So that's sort of like, that tells you how wrong maybe your period would be, or anything that you compute if you assume simple harmonic motion for this pendulum. Yes, question?
Someone asks, how is simple harmonic motion different from any other motion of the spring?
Yeah, well, simple harmonic motion is that cosine. So it's when the motion is exactly mapped out by the cosine curve. But there's lots of other kinds of oscillating motion that you can imagine. Maybe it would look like a triangle or something, or a square curve or something. But if the position versus time graph is exactly like a cosine, then we call it simple harmonic motion. And so, yeah, that's the idea, is that if we had more than 10 degrees, then the swinging of the pendulum would no longer be a cosine, and this would no longer be the period. You start to get it wrong. So 0.5% is like 5 thousandths, right? So if you're rounding your final answer to two significant digits anyways, that's like 100th. So a 0.5% error from your rounding or from your small angle approximation is never going to show up in your final answer. So I'd say 10 degrees. That's my reasoning. Okay. Physio contacted me. This is all these physics students that have a lounge in, I think it's MP217, and they are asking for first-year reps and all this stuff. And so what they want to do is have a study session. And I don't think they've completely planned it yet, so their location is TBD. But on the notes that I post, those PDF notes and the class notes, you can find this link, and you could click on it and just sign up for it if you're interested. They're going to do it sometime, does it say when? Some day before the final exam. They're not quite sure exactly when, but they know when the final exam is, and they're just going to ask you if there's any interest, then they'll try to do this. And so it'd be some people who'd already taken Physics 131, done well in it, and gone on to other physics courses, and might be able to give you some help and advice. So feel free to click in on that. Okay. This was one I was going to do last time, which is basically a pendulum problem from chapter 10. So Luke and Leah have a combined mass of 120 kilograms, and both grasp a rope of length 30 meters that is attached to a beam above them. And then they swing across a 10-meter horizontal gap. So I don't know if you've seen the movie, but basically there's a gap. There's no safety guardrails or anything like that, because they don't build those on Death Stars. But if you have a beam, there's a beam and there's a rope, then there's these people. They're the mass. Mass is 120 kilograms. And what they're going to do is they're going to swing in kind of a circular path around like that. And we're going to do the small angle approximation, which hopefully is okay, actually. 30 meters. This is 10 meters from here to here. This is the gap, I guess. And we're going to assume this is a pendulum. So what's the question? If they start from rest and swing down and up, just reaching the other side, how long does this take? So what we're going to do is, and by the way, on the Death Star, G equals 9.8 meters per second squared. Not sure why, but there you go. We're going to assume simple harmonic motion for this. And this comes up sometimes, even I think there was a question on MyLab and Mastering where there was a cart going along, or a tennis ball I think it was, and it hits the ground and then it acts like a mass on a spring, and then it bounces, and they ask you how long is the bounce? Well, and in that case, I think it turned out to be half of the period of simple harmonic motion. This is exactly the same thing here, is that if swinging back and forth would be the period. So half of that would be how long it would take for them to get from one side to the other. That's my reasoning. Would take the period t. And so a one-way swing is half of that. Should take time t over 2. So we're just going to use the equation for period, for pendulum, and divide by 2. That's the idea. It's 2 pi square root L over G. And then the time is t over 2. So it's pi square root L over G. So t is equal to 3.14 times the square root of 30 meters divided by 9.8. And I got 5.5 seconds. One thing we might check, basically, is the small angle approximation valid, which is what we just talked about. Well, if we think of this as being like theta max, I think if this is 5 meters and the hypotenuse is 30 meters, and this is a right angle, and this is theta max, I think we can find that sine of theta max is equal to 5 meters divided by 30. So theta max is like sine to the minus 1 of 5 over 30. And my fingers crossed that this is less than 10 degrees. I got 9.6. Ooh, that's close. 9.6 degrees. So since that's less than about 10, then I think rounding things to two significant figures should give us about the right answer. It's a 0.5% kind of error. Less than 0.5% error in period. Or the time we're trying to find. So it seems good. How are you guys doing on this? There was one more learning catalytics I wanted to do on resonance, I guess, and then that's it. We'll go into chapter 11. Discussion boards okay? Or? That's a good question. You can always use your mic if you want, and then you show up in the video as well. But Joanna is asking, do we always have to do the check, I guess, when we're doing the small angle approximation? I don't know. No, but I like to do checks to see if I'm getting it right. Yes? What if the small angle approximation doesn't work? Then you're out of luck. So yeah, that's a great question. What if the pendulum's swinging more than 10 degrees, right? So then you can't use simple harmonic motion because it's not simple harmonic motion, and you would have to solve it in a different way. It's kind of like saying, what if air resistance is important? You know, well, it is a lot of the time. If I throw a ping pong ball really far, air resistance is incredibly important, and so you can't use a parabola and all these. Quick little solutions. So the true answer is you would have to do a numerical simulation with the actual forces acting on the actual pendulum, and you wouldn't be able to use any of these equations. So that's a great question. Sometimes in physics, the problem is hard, in which case we don't study it in this class. But this one we can do. I wouldn't give that to you. All right. So yes, this was just, we talked about resonance, says that this is a plot of amplitude of eventual vibrations, maybe after you've pushed the kid on the swing for a while, there's some amplitude, versus the frequency of the driving force. So the amplitude goes up and down, and it's maximum at a special frequency called F0, where F0 is the natural frequency of simple harmonic motion. So it's the one that you would find from any equation like that of simple harmonic motion. So, for example, if you used T is 2 pi square root k over m, that would give you a period, that would give you a natural frequency, and that's where the thing will resonate. So here's the learning catalytics question from this is chapter 10 one. The last section of chapter 10 is on this resonance thing. So if there are some equally spaced bumps on the road every 10 meters, and the natural frequency of the shock absorbers in your car is 0.9 hertz, at what, driving now I mean like speed of the car, would you feel the bumps the most? So when would you find the resonance there? See if you can. Maybe I'll try to draw it. Bump, bump, bump. I'm also going to set a timer for a minute, so please discuss with your neighbor if you have a friend. It's actually your minute. Do you guys have an answer for me? Seem to be kind of working on this still, so let's give another 20 seconds. Maybe check your neighbor. Okay. 250 responses. One once, one twice, and let's see. A lot of people are saying 66% of you voted for 9 meters per second, C. So where did that come? So do you remember this old equation? For zero acceleration, the speed is the distance divided by the time, right? And so what we want to do is, I would say, for resonance to occur, t should be equal to like t, capital T. So basically this v is distance divided by capital T. So that's distance times 1 over t. So that's distance times the frequency. So I would say 10 meters is the distance between bumps. You're hitting them every 0.9 hertz, or that's the frequency you're hitting them, 0.9 times 10. So you get the speed is 9 meters per second. So that's kind of interesting. The hertz is 1 over seconds, right? And times meters gives meters per second. Yes, question?
There's another question on
Yeah.
the theta max. So how do you know that theta max is less than 0.5% error? And what is the parameter of error that you compare theta to?
Well, the idea is that the small angle approximation is you're saying sine theta equals theta. So that's not generally true. And so if you want to see what your error is, you can just subtract them. Sine theta minus theta. You get a really small number. And it's 0.5% is if your angle is less than 10 degrees. And so I'm just sort of assuming that since sine theta is within 0.5% of theta, that just setting them the same is going to make you sort of propagate, I guess, that error down with 0.5% of an effect, I guess, in your future numbers. It's a great question. That's my assumption there. Okay, I think we're done. I think we're going on to chapter 11 now. Last chapter we have to look at. But it's a fun chapter. It's all about waves. And the idea here is that sight and sound, these senses both rely on waves, very different kinds of waves. So sound waves are actually pressure waves in the air. So air molecules are filling this room at a high pressure. If the pressure changes because something moves, or my vocal cords or some speaker or something oscillates, then what will happen is that the particles will collide into each other and spread that pressure wave out, and actually it'll travel at 340 meters per second out into the air. Sound is a pressure wave which travels through the air. It turns out that light is a little different. Light is an electromagnetic wave. So you have the electric field and the magnetic field that's set up by some sort of oscillating electric charge. And when you move an electric charge, then accelerate an electric charge, then the effect of that change propagates outwards at 300,000 kilometers per second and affects the electric and magnetic field. So it doesn't need the air, but we can also detect it with our eyes. But in this chapter, we're talking about mechanical waves, such as sound, I guess. A vibration from chapter 10, I guess, is a periodic linear motion of a particle about an equilibrium position. But when many particles vibrate and carry energy through space, this is a wave. And a wave extends from one place to another. So you might remember us doing the wave a bunch of times back on those Wednesdays, sort of towards the beginning of the semester. And what was interesting is that I was measuring, I think, the speed of something, which is, all these people standing up and sitting down again. But there was no actual person running around the room at that speed. All any of you did, all you particles, I guess, was just stand up and sit down. But the influence of the wave, or the, I don't know, some sort of, if you were to maybe do an amplitude of the wave, or the crest, that sort of conceptual or abstract object did move with some speed. And so when we talk about wave speed, we're actually talking about the motion of that crest in the wave. So examples are water waves, light, which is an electromagnetic wave, and sound. And I've tried to draw a little circle, old circle here, which is trying to plot the motion of particles in a water wave. But basically, you see it all around. Like, look at this cat's tongue. It's disturbing the water because he's drinking some water, and that disturbance travels outwards as these ripples. So the medium here is the surface of the water, and some disturbance in one place will then will travel outwards. So, or maybe there's a beach ball. A beach ball gets dropped into the water. Well, what it'll do is displace some water into a little circular hill around it, and then that will move outward at some particular speed. So these are what are called two-dimensional circular waves, or wave fronts, I guess. So we call these little hills a wave front, and if you are on a two-dimensional surface, like a water surface, then these wave fronts are actually circles and they travel outwards. But in 3D, like if we have this black speaker right here, which is where I think my voice is coming from, then those sound waves are traveling outwards in all directions. So if I snap my finger or something like that, it sends a pressure wave out that's actually spherical. So if you have a point sound source, this red dot, producing sound waves, then the wave fronts would be these concentric spherical shells all centered on the source, and they would be going outwards at the speed of sound. So once again, a wavefront is the locus of all the crests at which the disturbance is maximum. So if you think of this as a sine wave, and it's going along the x-axis, for example, then it would look kind of like this. There'd be a crest, a trough, a crest, a trough, a crest, a trough, a crest. And these would be moving outwards. So what you're looking at is the locus or something of all the crests. So similarly, along the y-axis, there's a trough and a crest and a trough and a crest and a trough and a crest. So, these are all traveling outwards like that. And similarly along the z-axis, same sort of thing. It's going up and down and up and down. In all three directions, these things, or all directions, I guess, these waves are traveling out. And that's what you're kind of mapping, is you're mapping the high pressure points as being the wave fronts. Or similarly, if you're looking at light, then you'd be looking at the maximum electric field or something. Would be the wave fronts traveling out. And we'll do a demonstration of sort of how this works. If for a transverse wave, for example, the medium vibrates perpendicularly to the direction of the energy transfer. So example, vibration and stretched strings or musical instruments, but maybe. Thank you. There we go. So we have a little wave machine here, which what it is actually is it's a whole bunch of sticks that are all connected by a torsion wire in the middle, so that if I move one of these ends, so it sends a little wave rippling along. And so that's kind of the idea. It's like these particles are you, and if you stand up and sit down, you go, whoa, then that effect moves itself along at some speed, which is determined by how springy this medium is. But what's interesting is that you're actually transferring energy. There is something that moves, and if I, for example, if I was to, I could high-five myself from a distance. If I hit this thing here, like maybe like that, and then I feel the energy over on that side. So something has moved, some sort of influence, and what we think of it as is the energy has moved. So whatever input I put over here by hitting it, that influence has traveled along, and then it can do something over here. So for a sound wave, for example, if I speak over here, that's oscillating something, that's putting energy into the air. Then later, it oscillates your eardrum over here, and then you can hear me. Right? So that energy from my voice is going out, and then creating motion in your eardrum and affecting you that way. So that's great. Thank you. Cool thing. So that's the so there's a direction of energy transfer, which in this case is from left to right, and there's the direction of vibration. So that's the other interesting thing is if you notice, those sticks all move up and down, and yet that wave travels from left to right. So that's why it's called transverse waves, because they're perpendicular. But there's something called longitudinal waves where you can have the medium vibrating parallel to the direction of energy transfer. I don't know if it's possible to do this in here. So this one, I want you to stay in your seats. This is an experiment because I've never actually done this one before, but can we do a longitudinal wave? So what I want you to do, if you're starting the wave, don't stand up and sit down because that would be transverse. I want you to just shake back and forth like that and say, whoa. Does that sort of sound okay? And then if the person beside you is shaking, then you also shake. So just move. So the particles, you're just going to move side to side. Wait, don't do it yet. We're going to start over on this side of the room and then try to go this way. So 1, 2, 3. Whoa. Oh, so good. Okay. That's a longitudinal wave. So very good. So the particles are oscillating in the direction of motion. And what's interesting about longitudinal waves is that when you're shaking like that, you get kind of closer to and farther away from your neighbor sometimes. If you shake like left and your neighbor shakes right, then depending where your neighbor is, either you're going to get farther away, which is called a rarefaction, or you're going to get closer together, which is called a compression. So that is why the pressure goes up and down in a sound wave, is because the particles are, if they're closer together, that's higher pressure. And if they're farther apart, that's lower pressure. So it's one of the key aspects of a longitudinal wave is that it has these high density, low density, or high pressure, low pressure regions that travel out. So this, by the way, would be like the speaker oscillating back and forth. And then over here, this would be some sort of like column or tube of air. If you read all through chapter 11, you'll see we get quite a bit into these tubes of air. Okay. Let's do haven't done learning catalytics in a while, so let's do this. Which of these definitions best matches a transverse wave? A wave in which energy is transmitted in the opposite direction to the wave motion. B, a wave in which the energy is transmitted in the same direction as the wave motion. C, a wave in which the medium oscillates in a direction that is parallel to the direction of the wave energy travels. Or D, a wave in which the medium oscillates in a direction that is perpendicular to the direction of the wave energy travels. So you've got wave energy, and you've got the medium, and you guys are the medium, the particles. Take a minute to discuss. Check your neighbor. 10 seconds. Going once, going twice. And survey says most people are saying D, so that's the one I like. Transverse, meaning what we normally did. You stand up, sit down, and yet the wave energy travels from left to right. So that's what most of this chapter kind of has, is transverse waves. And that's what all these waves on a string are. So I want to talk about snapshot graphs versus history graphs. So, because this gets a little confusing, but a snapshot graph is pretty easy. What it is if there's a wave, like maybe on the wave machine or on a string or something, if it goes along and you take a photo of it and kind of freeze time, you would see the wave. It's literally a picture of the wave at a particular instant. So if you plot delta y versus x, that would be a snapshot. So it's sort of weird. What we've got is the displacement. I'm going to call that y. So y is a dependent variable. It's the dependent variable that goes up and down. It's like the, position of you as you stand up and down. And the independent variable is x. So actually there's, in a wave, there are two independent variables that can change. There's actually x, but there's also time. So a wave travels through space, but also over time. And so you have x and t determining what the y is. So one way of visualizing a wave is to look at multiple snapshot graphs and see what happens. Maybe that's kind of the easiest thing. So here's a figure. It shows a sequence of snapshot graphs as a wave pulse moves from left to right. So at time t1, it looks like this. At time t2, it looks like this. At time t3, it looks like this. So every delta t, the wave moves, the whole shape just shifts over. Delta x is v times delta t, where v is now the speed of the wave. And it keeps going here. Here's your little delta x. For every equal interval of time, delta t, you'll get that same shift. So the wave moves with a constant speed, which we're going to compute. So I could say maybe we'll call it the wave speed. V is equal to delta x divided by delta t. Okay, so that's good. So now we're going to do the history graph, which is what you do is you see this x1. Imagine you just think about the particle which sits at x1 at a particular place. And what if you were to make a plot of its position versus time graph? So just freeze the x and now look at y versus time. Well, at some instant t1, it's going to be here. Then at t2, it's going to be up here. At t3, it's going to be up there. You could just make plots of all these things at different times, and that's called the history graph. This one's a little harder to conceptualize, but it's just a position versus time graph of a particular particle on the wave as the wave goes by. So it's actually like your position. If you're standing up and sitting down, it's like the position of your head versus time as you stand up and sit down. This graph tells the history of a particular point in the medium. So you have to choose an x. So maybe this would be that T1, and then I think T2 was when it went over the hill. And then there was T3. I'm not spacing these all that well, but you get me, right? T4. For all these delta T's, it goes up, and then it comes back down again. And so there's like earlier times and later times. And what's kind of interesting is that if you look, you know how like in this graph, the steep side is on the left and the shallow side is on the right? It's the same one as this, where the steep side's on the right and the shallow's on the left. So it gets kind of flipped. Note that for a wave moving from left to right, the shape of a history graph is reversed compared to the snapshot graph. I don't know. Sort of makes sense if you think of the leading edge as being the first thing that gets to you and the trailing edge being later, right? So let's do learning catalytics. It's called pick the correct snapshot graph that corresponds to this history graph for t equals 5 seconds. So remember, a snapshot graph has to be at a particular instant of time. We're going to do that at 5 seconds, actually. And what we're showing here is a pulse that goes up and down. It travels in the plus direction, so from left to right. Where will this pulse be at t equals 5 seconds? Feel free to discuss with your neighbor. So by the left end of the rope, what it means is that that history graph is at the x equals 0 point. Okay, that's the left end. Okay. So this one's a hard one. We'll maybe pick a graph, and so I can discuss it. Going once, going twice. We'll see what survey says here. So this didn't go so well, but there are some of you, I feel like more than 25% of you answered what I think is right, which is D. So let me try to kind of describe what I was thinking there. Is that, so first of all, delta x is V equal to V times delta t, right? So delta x is going to be, I guess, like if this is 3 seconds, delta t is 3 seconds for the pulse. Then I can say that delta x is going to be like 6 meters. So I need something that's 6 meters wide for sure. That's one thing. So I think this isn't going to work since 5 minus 8 is 3. So that rules out B right there. So that's one thing. This steep edge, by the way, is later. It's at t equals between 2 and 3. So what that means, so it is trailing, right? It's going to be at the end of the wave. So I think that that rules out A. It's got to be C or D. So then the question is that this trailing edge at 3 seconds, so trailing edge is at x equals 0, which is what that whole history graph is about, at t equals 3 seconds, right? So at t equals 5 seconds, which is what these snapshots are supposed to be about, this trailing edge should be at 10 meters. At x equals 10 meters. So does that match anything here? Wait. Yeah, sorry. You're absolutely right. So this is the x equals 0, sorry, this leading edge, sorry. This leading edge is what I'm talking about. Is that at x equals 0, t equals 3 seconds? Yeah. Wait, no, that's not quite right. Yeah, t equals 0 seconds. So at 5 seconds, it should be at x equals 10 meters. Sorry. Because it's going 2 meters per second. Messed that explanation up a little bit. So I would just want to talk about sinusoidal waves, and we'll try to do one on the wave machine, I guess. But you can put in any shape that you want. And so let's do it first, actually, on the wave machine, is that we've been sending pulses. Well, what if I send, instead of just one pulse, what if I just oscillate this, the right end, well, let's do the left end, actually, with simple harmonic motion. If I oscillate this up and down with simple harmonic motion, then I get a wave that just travels along, and then it reflects off the end. So this gets kind of complicated because the medium doesn't extend infinitely, but you can imagine, if it did keep going, that I would have a sine wave that would travel along for a long time. And that's called a sinusoidal wave. Raphael? Yeah. So standing wave, which is later in the chapter, is when you just allow the reflections to come back and forth. And you get these nodes. It's a little hard to see it. You have to pick just the exact right frequency, and then you can get this whole thing. There we go. That's kind of a good standing wave. I don't know how many nodes there. Let's do a lower frequency standing wave. What if I just go up, down, up? That's sort of also a standing wave. Okay, good. So what I want to do is move on to cosine is a shape that a wave can have. So we were doing triangles. Well, triangle is one shape. Also, cosine is a shape. So you can, these equations look kind of nasty because there's two independent variables, lowercase t and lowercase x. And there's a new letter here called lambda. This is called the wavelength. But now we have a sinusoidal wave. So the period, capital T, is the time for that wave to complete a whole vibration at any point in the path. The frequency is 1 over t. And the amplitude is the maximum distance that any point in the medium goes away from its equilibrium position, so the delta y, I guess, there. And the wave speed turns out to have an equation that it's v is equal to lambda divided by capital T. The wavelength divided by the period gives you the speed that waves travel. And so, so you have to imagine, like, if you go, whoa, 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 and so each one of you is oscillating like a simple harmonic motion up and down, like a, I don't know, mass on a spring or something, and it just keeps going along. So this is a snapshot graph showing the instantaneous velocity. If you're your maximum standing up, you stop. If you're at equilibrium, you're kind of going as fast as you can down or as fast as you can up as this wave travels from left to right. So as a wave moves along x, the velocity of the particle in the string is in the y direction because it's a transverse wave. So for this one, this will be our last question here. See if you can draw it, the direction of the motion of this particle on this sinusoidal wave at this instant. So, and the way that I do this in my head, because this is a tricky question. So first of all, it's a transverse wave. So that tells you that the direction has to be up or down, I think, right? And then the second thing is that what I try to imagine is that it's the pattern of the wave that is moving from left to right here. And the particle's job is to stay on the pattern, right? So if a little later the pattern's going to be above you, you're going to have to be moving upwards or something. So, or if it's going to be a little below you, you're going to have to be moving downwards. So sketch an arrow. Length doesn't matter, only the direction. I'm going to see what it looks like from your guys'. Looks like you can just kind of, with your mouse or your finger, drag along an arrow. Like I said, length doesn't matter, just try to get it the right direction. Okay, you guys got an arrow direction? See what people are saying here. Going once, going twice. It's a little harder to submit. Let me just show what's going on the screen here. It's all over the place. A lot of people are voting down, some are voting up. So what I like is, send all. One way I look at it is that, remember, this is what the wave, you're doing a snapshot of a wave that looks something like this. And so there's a pattern that is moving along. And this is like maybe now. So maybe if I go to green or something, I could do a little later. Does this make sense? Later. Like just delta t later, a little bit later. So if you're this particle, you now have to stay on the wave because a crest is approaching. So the only way for you to do that, I think, is if your velocity is up at that point. And you're always at, since it's simple harmonic motion and you're at equilibrium, you're always at your maximum velocity. So I think velocity is up. As the particle crosses equilibrium. So that's sinusoidal waves, which I'll continue with when we come back on Friday. The other thing I'm going to talk about on Friday is the decibel scale and reflections of waves. We can talk a little bit about that, echoes and things like that. So see you then.